Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 46. In this lecture, I want to solve a couple of practice problems so that we can better understand angular motion. These topics are covered in chapters 10 and 11 of our textbook by Surway and Jowett. Before turning to our practice problems, let me review some of the ideas that we have learned. Over the last couple of chapters, we've learned that there are two types of motion. There is linear motion and there is angular motion. Linear motion is also referred to as translational motion. Angular motion is also referred to as rotational motion. In the case of linear motion, all points on an object have the same velocity at any given time. So every atom of an object in linear motion is moving with the same velocity vector. That velocity vector may change from one moment to the next, but at any given moment, at any given instant in time, all points on an object have the same velocity vector if the object is engaged in linear motion. In the case of angular motion, the situation is more complicated because different points on the object can have different velocity vectors. The velocity of individual atoms of an object that is engaged in angular motion could point in different directions or even have different magnitudes. This is an important difference. Nonetheless, there are some important similarities or analogies between the two types of motion that you should be aware of. Understanding these similarities will help you to better understand these new quantities that we've learned about over the last couple of weeks. For example, we talk about the linear position of an object, and if that position is changing, we'll talk about the linear velocity of the object, which is the derivative of x with respect to time. And if the velocity is changing, then the rate of change in velocity is acceleration. Similarly, when an object is rotating, we talk about its angular position. And of course, if the angular position is changing, we're interested in knowing how fast it's changing. We're interested in knowing the rate of change in theta, in which case we talk about angular velocity. And if the angular velocity is changing, that rate of change is denoted by alpha, the angular acceleration. In the linear world, mass was an important quantity for us because mass told us how difficult it was to accelerate an object. An object that has a large mass is going to be difficult to accelerate or decelerate. So mass is a measure of the resistance of an object to linear acceleration. In the angular world, the analog is inertia. Inertia is what tells us whether it's easy or difficult to angularly accelerate an object. If you have a disk and its moment of inertia is small, then it's going to be very easy to angularly accelerate that disk. If its moment of inertia is large, then it's going to require a lot of force or a lot of torque to accelerate that disk. Objects in motion can have energy. We call this energy kinetic energy. If the motion is linear, then we have linear kinetic energy. If the motion is angular, we have angular kinetic energy. And of course, you can have both types of energy at the same time. The thing that brings about linear acceleration, the cause of acceleration, is force. The thing that brings about angular acceleration, the thing that makes things spin up or spin down, is called torque. We found that in the case of linear motion, there's a special quantity which we call momentum, and we denote using the letter P. Under the right conditions, this quantity is conserved, and that's a very useful idea. Similarly, there is a conserved quantity called angular momentum, which we denote using the letter L, and under the right conditions, this quantity is conserved in angular motion. So we can use this quantity in the same way that we use this quantity to figure out the final velocity or angular velocity of an object. To add a little detail to the analogies that we were discussing on the previous slide, here I want to list some important equations. On the left, we have the important linear equations, and on the right, we have the analogous angular equations. So velocity is the derivative of position with respect to time, just as angular velocity is the derivative of angular position with respect to time. From a physical point of view, angular velocity and velocity are two different things, but from a mathematical point of view, they're quite similar. The algebra or the calculus that's involved in solving for these quantities is almost exactly the same. Acceleration is the first derivative of velocity or the second derivative of position with respect to time. Similarly, angular acceleration is the first derivative of angular velocity or the second derivative of angular position. An object in motion is going to have energy. We call that energy kinetic energy. If the object is executing linear motion, then the kinetic energy is 1/2 times a measure of the resistance to linear acceleration times the square of speed. For angular kinetic energy, we have similarly 1/2 times a measure of the resistance to angular acceleration times the square of the angular speed. Newton's second law of motion tells us that there's an important relationship between force and acceleration. The two are related by this equation. And the angular second law of motion, although it's not due to Newton, the analogy is quite obvious. It tells us that there's an important relationship between torque and angular acceleration. Momentum is a conserved quantity. If we're talking about a point particle, we take the mass of the point particle and multiply it by the velocity of that object. If we're talking about an extended body, like a chair, something with arms and legs, something complicated like maybe an airplane or a cat, if we're trying to calculate the linear momentum of that object, we need to take its total mass and multiply it by the velocity of its center of mass. Different pieces or parts of the object might be doing different things, but if we can figure out the velocity of its center of mass, then we can multiply that by its total mass, and that gives us the linear momentum of that object. For angular momentum, again, we have two formulas. They're quite different. If you're talking about the angular momentum of a point particle, you need to take its position vector and multiply it by its momentum vector. And of course, remember, this is not ordinary multiplication. This is vector multiplication, or the cross product. On the other hand, if you're talking about an extended object like an airplane, then you need to calculate the moment of inertia of the object and multiply it by its angular velocity. Force and momentum are related to one another. If there are external forces, then the momentum will change. If the sum of all external forces is equal to 0, then the momentum will not change. Its derivative will be 0, so we can say momentum is conserved. Similarly, torque and angular momentum are related. If there are external torques acting on a system, then its angular momentum is going to change. But if the net external torque is equal to 0, then the angular momentum is going to be conserved. It's going to be constant. It's not going to change in time. Let's do a practice problem now that uses some of the ideas we've been discussing. A rod of length L and mass m is pivoted at its left end as shown. The rod is free to rotate about the pivot point, subject only to gravity. It is initially at rest. Calculate the rod's angular speed when it is vertical as shown. So we have a rod that is pivoted at point O. What that means is that this point of the rod cannot move, but the rest of the rod can rotate freely about point O, about the pivot point. The rod begins in the horizontal orientation, but of course gravity pulls it down, so it's going to, in a sense, fall, although this is not free fall, so the acceleration is not going to be 9.8 meters per second squared. It will fall and it will accelerate, it will build up speed, and we want to know what its speed is when it is vertical. The rod might swing past this vertical orientation, but for us the problem ends here. We want to know how fast the rod is rotating. We want to know its angular speed when it has rotated through 90 degrees. Now, ordinarily, when someone asks for the speed or the angular speed of an object, One strategy for calculating or solving for the speed is to use kinematics. You could use the linear kinematic equations to find v, or you can use the angular kinematic equations to find omega. Of course, in both of these cases, there is a caveat. The acceleration or the angular acceleration must be constant, otherwise you're not allowed to use the kinematic equations. Hopefully, this problem looks somewhat familiar to you from one of our previous lectures. In that lecture, we actually calculated the angular acceleration of this rod, and we found that the angular acceleration of the rod is not constant. Since the angular acceleration of this rod is not constant, we cannot use the kinematic equations to find its final angular speed. So the second strategy for finding speed is to use conservation of energy, and that's exactly what we'll do here. Of course, before you use conservation of energy, it's a good idea to have a coordinate system, because after all, we'll be interested in knowing, for example, the gravitational potential energy of the rod. And to calculate that quantity, we need to know the height of the rod. More precisely, we need to know the height of the center of mass of the rod relative to our coordinate system. You can put the coordinate system anywhere you want, but perhaps the easiest choice is to choose a standard XY coordinate system with its origin at the pivot point. So what we're imagining is just a standard XY coordinate system with its origin, with its 0, 0 at the pivot point. That's a convenient choice because the pivot point does not move, and so it makes sense to put the origin there, although you don't have to. This just happens to be the simplest choice. Now that we have a coordinate system, we can talk about energy, and we can calculate the energy in terms of L and M. We'll want to figure out the initial kinetic energy of the system. The initial kinetic energy is going to be the initial potential energy plus the initial kinetic energy, and that will equal to 0, because initially the rod is at rest, so it has no kinetic energy. And if I asked you what's the height of the rod, more precisely what's the height of the center of mass of the rod, you would say the height is 0. So mgh, which is the gravitational potential energy, would be 0. So really the initial mechanical energy of the system is simply 0. Now let's talk about the final mechanical energy. Finally, the object will have some potential energy. It has swung through 90 degrees. Its center of mass is no longer here, but it is over here. Remember that for a uniform rod, the center of mass is at the geometric center of the object. So we can say that the center of mass is length L over 2 below the origin, which means that the height is negative. If we wanted to know what the y-coordinate of this point is, we would say that the y-coordinate for the center of mass is equal to minus L over 2. And therefore, when we talk about the final potential energy, we're going to say that it's mgy. We have m here, we have g here, and then we have minus L over 2 for the y coordinate. So the final gravitational potential energy of the rod is going to be minus mg L over 2. What about the final kinetic energy? Well, this object is obviously rotating, so it's going to have rotational kinetic energy or angular kinetic energy. Recall that angular kinetic energy can be calculated using this formula. K angular is equal to 1/2 I omega squared. At this point, you need to look up the moment of inertia of a rod that is rotating around one end. And if you look that up in your textbook, you'll see that the moment of inertia is 1/3 mL squared, mass times length squared, divided by 3. Which means that the angular kinetic energy of the rod as it is rotating is going to be 1/6 mL squared times omega squared. Now, we don't know what omega is, but omega is exactly the thing that we're trying to solve for. We want to calculate the rod's angular speed, which is this omega here. According to conservation of energy, we can set these two equal to each other. Notice that in this case, there is no friction. We're ignoring drag, so we can easily say E initial is equal to E final, which means this entire quantity here is going to be equal to 0, and then we can proceed to solve for omega. With a little bit of algebra, you will see that omega is equal to the square root of 3g over L. Let's do another practice problem. A merry-go-round, which can be modeled as a disk, has mass 1,000 kilograms and radius 3 meters. Alice, which can be modeled as a point particle, has mass 60 kilograms and stands on the merry-go-round at 3 meters. Alice and the merry-go-round rotate with initial angular speed 2 radians per second. Alice walks slowly towards the center. What is the angular speed when Alice reaches 0.5 meters? So what we have here is a simple merry-go-round, which is essentially a disk that is spinning around an axis of rotation through its center. This is not a powered merry-go-round. This is not one of those fancy merry-go-rounds with horses that go up and down, playing annoying music with motorized motion. This is not a motorized merry-go-round. A person has to push this merry-go-round to get it to go around, basically. Now, the merry-go-round itself is a relatively heavy disk. Alice, on the other hand, who's standing on the edge of this disk, is relatively light and also relatively small. So we will treat Alice as if she's a point particle when compared to the much larger merry-go-round. Initially, Alice and merry-go-round are spinning together with an initial angular speed of 2 radians per second. However, when Alice begins to walk towards the center, the merry-go-round begins to spin up. It begins to speed up, it begins to go faster. The question is, how fast will the merry-go-round go when Alice reaches a distance of 0.5 meters from the center? Now, before getting into the details of this problem, you might want to just ask yourself why the merry-go-round would speed up when Alice is walking towards the center. This is not a motorized merry-go-round. There is no outside source of energy or force or torque that is pushing this thing. Nonetheless, the merry-go-round speeds up. Well, if there are no external forces or torques on this system, then we can say the system is isolated. And if we're saying the system is isolated, then we're essentially saying that the angular momentum of the system is conserved. So we're essentially saying L initial is equal to L final. Now, when I say system, what I really mean is the merry-go-round and Alice together as one system. Now, remember what angular momentum is for extended bodies. Angular momentum is the moment of inertia times angular speed. Think about what happens as Alice moves towards the center. As Alice moves towards the center of the merry-go-round, she's basically changing the distribution of mass within the system. In fact, as she gets closer to the center, the moment of inertia decreases, so we can represent that by a down arrow. But of course, we want the angular momentum to be conserved. We want it to stay the same. We'll represent that using a dot. Now we have an equation here, and you should be thinking, if the left side is constant and on the right side inertia is decreasing, then omega must increase. The angular speed must increase to compensate for the decreasing inertia. From a different point of view, you can say that as Alice is walking towards the center of the merry-go-round, she's using the friction between her shoes and the surface of the merry-go-round to walk. Without that friction, she would not be able to walk. It turns out in that act of walking, the surface is exerting a force on her, that's the force of friction, but she's exerting a force on the merry-go-round. It turns out the force that she's applying to the merry-go-round with her feet is ultimately responsible for spinning up the merry-go-round. Let's make all this much more precise. Let's begin by calculating the moment of inertia of the system. When I say the system, I mean the merry-go-round and Alice together. The merry-go-round is a disk, so at this point you turn to your book and you find the moment of inertia of a disk, which turns out to be 1/2 mr squared. And we're treating Alice as a single point particle. For a point particle, the moment of inertia is simply mr squared. So the sum of those two gives us the moment of inertia of the entire system. To calculate the initial angular momentum of the system, we need to multiply the initial inertia times the initial angular speed. The initial inertia is going to be 1/2 mr squared plus mr initial squared, r sub I is the initial position of Alice, times omega initial. We have all of these quantities. The mass of the merry-go-round is 1,000. The radius of the merry-go-round is 3. Little m is the mass of Alice, which is given to us as 60, and her initial position is 3 meters. The initial angular speed of the system is 2. Multiplying all that out, we find that the initial angular momentum of the system is 10,080 kilogram meters squared per second. We can now turn to the final angular momentum of the system. The final angular momentum is going to be I sub f times omega sub f. Omega sub f is the thing we're after. We'll solve for that. And I sub f is the final moment of inertia of the system, which is the final moment of inertia of the disk plus the final moment of inertia of Alice. The disk is not really changing here, so its moment of inertia is simply 1/2 mr squared throughout the problem. Alice is changing. More precisely, her distance to the center is changing. Her final distance is 0.5 meters. Plugging all that in, we find that the final moment of inertia of the system is 4515. And since the system is isolated, since there's no one pushing or pulling or exerting any kind of a torque on the system, we can say angular momentum is conserved. Therefore, the initial is equal to final. Setting those equal to each other, L initial is equal to L final, we find that the final angular speed of the merry-go-round Alice system is 2.233 radians per second. So as we suspected, the merry-go-round speeds up as Alice walks towards the center. Let's continue the same practice problem. Part B asks, calculate the initial and final kinetic energies of the Alice merry-go-round system. Remember that kinetic energy is 1/2 mv squared in the case of linear motion. In the case of angular motion, which is what we have here, this is rotational motion, the kinetic energy is 1/2 I omega squared. The initial kinetic energy is 1/2 initial inertia times initial angular speed squared. Initial inertia squared is 1/2 mr squared, which is the inertia of the disk or the merry-go-round, plus Alice's initial inertia, which we're treating as a point particle. Omega initial was given to us as 2 radians per second. We can plug all that in and we find that the kinetic energy of the system initially is 10,080 joules. If you want, you can break that up into 2 pieces. You can say the merry-go-round has a certain amount of kinetic energy, Alice has a certain amount of kinetic energy. You can calculate those separately and you would get the same final answer. So this is the initial kinetic energy. What about the final kinetic energy? Well, once again, we use 1/2 I omega squared. The I, again, has to be the inertia of the system, so merry-go-round plus Alice. We found that out in part A to be 4515. We're going to multiply by the final speed, which we also found in part A of this problem. And when we put it all together, we find that the final kinetic energy of the system is 11,252 joules approximately. Again, you can separate that into the energy of the merry-go-round and energy of Alice, and then add those together with the same final result. Now, this result might seem a little strange. After all, Alice is walking towards the center, and in doing so, magically, or almost seemingly magically, she's speeding up the merry-go-round without any help from an outside agent. And clearly, the kinetic energy of the system is increasing. The system started with roughly 10,000 joules of energy, and it ends up with roughly 11,000 joules of energy. So where does this energy come from? How is it possible that the kinetic energy of the system magically increases? Well, the simple answer is that it's coming from Alice. Alice is actually pushing on the merry-go-round as she walks towards the center. It turns out walking towards the center of a spinning disk is actually difficult. She's going to find herself a little bit tired when she reaches the center of the disk. Her muscles will be performing a certain amount of work on the merry-go-round. In fact, you can calculate the exact amount of work that she performed by looking at the difference between the final kinetic energy and the initial kinetic energy. So the simple answer is that the additional kinetic energy is simply coming from Alice. Alice is burning calories. She's converting the chemical energy that she has stored in her body or in her muscles to the rotational kinetic energy of the system. For a more detailed look, you can divide the initial kinetic energy and the final kinetic energy into components belonging to the merry-go-round and Alice, and then you could see how the angular momentum and the kinetic energies are divided and how they change. And that's the end of this lecture. Thank you for your attention.